Okay, I'm recording. Okay. Hi everybody. We're gonna go ahead and get started with the MAE 201 Statics Exam 1 review. And then it's gonna be me, Lena, Luca, and Rocco. So the agenda is gonna be going through equations you need to know, how to set up the problem. We're gonna do 5 example problems with solutions, and then we're gonna have open discussion. Okay, so for equations worth knowing for MAE 201, your main focus is that you always want to know for this class, your sum of the forces is going to be equal to 0, and your sum of the moments is going to be equal to 0, and how that's going to be broken up to just the sum of the forces in the x, y, and z direction. I believe for exam 1, you kind of start going into the z direction, but initially in the very beginning, you're just doing x and y, but you also have the forces in the z direction, and then the same thing for the moments. Your sum of the sum of the moments is just going to be 0 about your axes. So how you want to set up your MAE 201 problems, you want to read and underline your key givens in the problem statement. You want to define your axes and your origin and draw them out in your free body diagram, which gets to the next point, which is just drawing your free body diagram. And then you want to write out your equilibrium equations and then solve for your unknowns. So we're going to go ahead and get started with the first problem.
Okay, so this is the first problem we got. It's a 2D beam fixed with a pin and a roller at A and B. So first I'm just going to draw this out. We'll draw our pin connection here and a roller at A. And at A, there's a 300 Newton force applied vertically. At this end here, there's a 650 Newton force applied at an angle of 30 degrees. And at this point here, there's a 500 Newton force applied at an angle of 60 degrees from the horizontal. We'll also write out our distances. Ignore the scaling, that's way off. And there's also a couple moment here, 1500 Newton meters. All right. So the first step in this problem is going to be drawing out our coordinate system. Standard for this class is to have positive x in the right direction and positive y going vertically upward, meaning z is coming out of the page. All right. And the next step is going to be to sum forces in the x and y directions. So first I'll sum forces in the x direction. That's going to get me 650 times the sine of 30 minus 500 times the cosine of 60. That's going to give me a 75 Newton force in the x direction. I'll do the same for the y direction now. That's going to be negative 650 cosine 30 minus 300 and then minus 500 sine of 60. All right, and we'll calculate that out. That's going to give us a negative 1295.93 Newton force, and that's going to be going downwards. All right, so now that I've got my sum of forces in the x direction and the y direction, I'm going to take a magnitude and solve for the resultant force. So the way that I'll do that, I'll say Fr equals Fx in the I hat plus Fy in the j hat direction. So I'll just express those here. This is equal to Fy. All right. Now to get the magnitude of this, I'm just going to take the square root of fx squared plus fy squared. That's going to give me a magnitude of 1298.1 newtons. All right. After that, I'm going to have to find the angle that this occurs at. So to do that, I'll say theta equals the inverse tangent of the force in the y direction over the force in the x direction, right? Because we know that tangent is opposite over adjacent. So it's going to be Fy over Fx. That'll give me a theta of negative 86.688 degrees. All right, and we know that's in the negative direction because the direction of our y force is downward, direction of our x force is in the positive direction. So that's going to give us a resultant negative 88. Did I draw that right? It's flipped. Sorry. How do I erase that? I'm kind of out of space here. Thank you. All right, the final step for this problem is to solve for that resultant moment. So I'm going to take a sum of moments about point B. That's this point here. So the first thing I'm going to do is take that 650 Newton force times the cosine of 30. And that's going to be multiplied by a distance of 3 plus 5 plus 2. All right. Now I'm going to add that 300 Newton force that's applied vertically downward times a distance of 5 plus 2 meters. I'm also going to add this 500 Newton force that's at an angle. So that's 500 times the sine of 60 times 2 meters. All right. And I'm also going to add that 1500 Newton meter applied moment that's applied at point A. Adding all these together should get a sum of moments about point B. We can also call this the resultant moment about point B of 10,095.19 Newton meters. All right. So for our final answers, we can write FR equals 1298.1 newtons at an angle negative 86.688. And then our resultant moment at B is 10,095.19 Newton meters. All right. All right, and that should set us up for the next problem. So this one's very similar. It's just in 3D. So the way that I'm going to solve this one is by using vectors. That should simplify the math a lot more so I don't have to do this like calculation here with the moment where I'm multiplying like that. I just take cross products. All right. So the first step in this problem is to express my forces and my moment arm radii or my radiuses in vector form, so Cartesian vector form. And I'll do that right here. The first one, we can see that that's only applied in the z direction. So right, 0 I hat, 0 j hat, and that's in the negative z direction. So I'm gonna write negative 300 in the k direction. And those are all newtons. For my F2 vector, I can see that that's only applied in the y direction. So 0 I hat, and that's in the positive y, so 200 j hat, and then nothing in the z direction. And then finally for F3, they actually gave that to us as negative 200 I hat, 500 J hat, and negative 300 K hat, also newtons. And now comes the tricky part of writing the moment arms for each of these. So since they want us to take the couple moment at point O, that's this point here, we're actually going to be taking arms, lever arms from that point to the point where the force is being applied. So I'll draw those out. Make it a little. So this one here is R1. This one here, R2. This one here is R3. And so they've actually made it kind of easy for us. If you notice, none of these R vectors have any components in the Z direction. They have no K components. So everything's just going to be in the X and Y. I'll write those out here. For R1, we see that this is only in the Y direction. So we'll have 0x, and that's a positive 2. So I'll write plus 2j hat. And again, nothing in the Z direction. And these are all in meters. For R2, this one's a little bit trickier. So I've got this 2 meters here, and then this 1.5 meters. So I'll add those up. It's going to be 3.5. And again, that's in the Y direction. For the X direction, we can see that this only goes over 1.5. So it's going to be a 1.5 in the X direction and a 3.5 in the Y. Again, with nothing in the K direction, nothing in the Z direction. All right, now for R3, we can see that this one in the Y direction goes over 2 meters. And in the X direction, it's also going over 1.5. So we'll express that as 1.5 I hat plus 2j hat, and again, 0k hat. All right. After that, we're going to sum forces to get the sum of forces in the X, Y, and the Z direction, and that will allow me to get the resultant force. So I can say sum of forces is equal to FR. And again, these are vectors. Equal to the vector F1 plus the vector F2 plus the vector F3. All right, so now I can write that out. 0 I hat, 0 J hat, negative 300 K hat, plus 0 I hat, plus 200 J hat, 0 K hat, negative 200, 500, and negative 300. And remember, when we're adding vectors, we're adding the components, right? So I'm not just adding these up. I'm not just doing negative 300, 200, and then negative 200, 500, negative 300 all added up. I'm adding the K components together. So I'll have the K hat components. Here I'm adding the J hat components, so the Y components. And here I'm adding the I hat components or the X components. And that's going to give me negative 200 in the I hat direction. It's positive 700 in the J hat direction and negative 600 in the K hat direction. And again, these are all newtons. So that'll be my final answer for the resultant force in vector form. All right. And I'll just circle that here. And now that leaves us with solving for the moment. So this is a little bit trickier because it requires us to use cross product. I'll write here M equals R cross F, right? So the sum of moments is going to be the sum of the R's cross the F's. And again, that's in vector form. So that's going to give us R1 cross F1 plus R2 cross F2 plus R3 cross F3. All right. So now I'll write this all out. I hat, J hat, and K hat. And then I'll just express my R's here. So R1, I've got 0, 2, and 0. My F1, I have 0, 0, and negative 300. I'll add that with the resultant moment for force 1 and for force 2 and for force 3. So my R2 is 1.5, 3.5, and 0. Then my F2 is 0, 200, and 0. I'll add that to the moment at 0.3. It's 1.5, 2, 0, negative 200, 500, negative 300. All right, and this is where most people will get stuck or have errors when they're performing this cross product. So I can actually write this out. For this one, in the I hat, if I ignore this row, I take the cross here, that's a negative 600 minus 0. So I'm not going to write that. Negative 600 I hat. Now I'll do oops, 2, 0. So now I'm going to do the J row. That's the eraser. There we go. Okay. So now I'm going to do J. That's going to be 0 times 0. So that's 0 in the J hat direction. Now I'm going to do K. So I'm going to take this here, 0 times 0, and then 0 times 2. Again, that's going to be 0. Hello. Hi, tweaking. Ah, thank you. 0K. All right. So that means this block here is just negative 600 I hat. Now we can do this block here, and I'll move that over there. For the y direction cross product, I'm going to have 3.5 times 0 and 200 times 0, 0 times 0, 0, or sorry, 0 plus 0, 0. For the j direction, I'm going to have 1.5 times 0, that's 0, 0 times 0 is 0. Again, that's going to be 0. And for the k direction, I'm going to have 1.5 times 200 minus 0 times 3.5. That's going to give me, what is that? 300. So I'll write that out. 0 in the I hat plus 0 in the j hat plus 300 in the k. All right. Now for the final one, same process here. I'll take the I cross product. 2 times negative 300 is negative 600 minus 500 times 0 is 0. So that just leaves negative 600 in the I hat. For the j, I'll do 1.5 times negative 300 minus 200 times 0. And again, we have to note that for the j, we automatically have a negative on there. Forgot to write that here. But these are automatically negative. And that's just a rule of the cross product. So I'll have 1.5 times negative 300, that's 450. So yeah, 450 and that's negative. All right, now for the k direction. I've got 1.5 times 500. I'm actually going to give myself some space here. For the k direction, I got 1.5 times 500, and then minus negative 200 times 2. More space. All right. Now adding all of these up, and again, we're adding vectors here, so we've got to add the components. That's going to leave us with a negative 1200 in the I hat plus 450 in the j hat plus 1450 in the k hat. And this is all going to be in Newton meters since we're multiplying a radius times a force, where our radii are in meters and our forces are in newtons. So that gives us the final answer. And that's about 0.0. All right. Yeah.
Okay, so we're gonna get started with this problem. So here we have a structure OAB is subjected to a force P, as shown in the figure. Calculate the magnitude of the force P if the moment it generates about the axis AG is equal to 1020 Newton meters. So I'm gonna go ahead and start by like highlighting. So we have a force P, and then we have um here we have our magnitude or our moment is 1020 Newton meters. And then we have the axis AG that we're trying to find the moment about. So first we're going to look at the structure over here. Kind of like we said before, we want to define our axes. So here we just have just the regular, probably should draw this a little bigger. So we have, this is a 3D structure. So we have Z of Y, we have X. Okay, I'm gonna go ahead and redraw this. Try my best at least. So we have this, and then we have this. Oh, so A, we have B, and then this is our origin. And then we have, let's see, try to make this a little more colorful. Let's see. So this is going to be 3 meters, and then this is going to be 5 meters. And then we have basically, just trying to think, maybe I don't draw the free body diagram because it might just look a little messier. Yeah, I think I'm just gonna stick to their diagram here, just because me redrawing this is gonna just look too messy. But we want to keep in mind that this is our origin, so this is where we're gonna be finding the coordinates of these points from. So we'll get started with point A, and that's just gonna be 0, 0, 3. And then we're gonna do point B, and that's gonna be 0, and then 5, 3. And then point C is gonna be 2.5, 2, 0. And then point G is going to be 2.5, 0, 0. Okay, so now that we have all of our points here, we do know that here they said in the problem, so calculate the magnitude of the force P if the moment it generates about the axis AG is equal to 1020 Newton meters. So what we want to do is we want to find this AG over here. So how we're going to do that is we're going to find first, we're going to solve for the unit vector AG. And how we're going to do that is we're just going to do this, the coordinate, and then divide it by the magnitude of AG. So we have 2.5 minus 0, so that's 2.5. And then we have 0 minus 0, that's 0. And then we have 0 minus 3, that's going to be -3. And then we're going to do the square root of 2.5 squared plus 0 squared plus -3 squared. And that's going to give us 0.640 and -0.768. So that's for the unit vector for AG. So now we're gonna find the force direction along BC. So that's this one. And here we're gonna do solving for the unit vector P. So we're gonna do BC divided by the magnitude of BC. So here for BC, that's going to be 2.5 minus 0, so that's 2.5. And then 2 minus 5, that's -3. 0 minus 3, that's -3. And then we're going to divide by the magnitude. That's 2.5 squared plus -3 squared plus -3 squared. And that is going to give us 0.508, -0.609, -0.609. So now we want to look at the position vector from A to B. And in that case, it's just going to be the distance between these 2 points. They're along the same Y and Z. Or sorry, yeah, the same Y and Z, but different X. Or no, sorry. They're along the same X and Z, but different Y. So here, the position vector is going to be 0, since we're not moving anything in the X direction, but we're moving 5 in the Y direction, and we're not moving anything in the Z direction. So now we're going to do, basically we're going to calculate the moment about the axis AG, which is what they want us to find, but we need to eventually solve for the force P. So in order to take the moment about this axis AG, we need to do the unit vector AG dotted with the position vector times the force. So in that case, it's going to be the unit vector of axis AG and then dotted with R cross the P force with the unit vector of the P force. So in which direction it's basically acting. So we're going to set it up kind of how the previous problem was set up with taking the cross product. And that's just going to be setting up I, J, and K. And then here we have 0, 5, 0 for our vector, basically the distance AB. And then here we're going to have 0.508, -0.609, and -0.609. And that's going to be our unit vector for the force P. So then once we do that, we're going to be doing just regular cross product. So that's going to be taking the I, and then we're going to have, let's see. So it's going to be one second. Oh. Okay, sorry, continuing. So we're going to do the cross product here. So we're going to hold on to I, and then we're going to do -0.609 times 5. And then this is just going to be 0, so we're just going to keep that term out. And then we're going to have -j, and that's going to be 0 in this case, since we just have, we're going to hold on, this is going to be multiplied by this, and this is going to be multiplied by this. So that's just going to be 0. So moving on to k, we're going to have this first term, these two multiplied by each other is going to be 0, but then we have negative, and then 5 multiplied by 0.508. So, okay, this gives us negative 3.045 in the I direction, and then plus 0 in the J direction, and then minus 2.540 in the K direction, which can also be written out as negative 3.045, 0, and negative 2.540. Okay, so we're still not done yet because that was just doing this part, the cross product. So now we want to do the dot product with this. So I'm gonna go ahead and just copy this. Maybe? No? Okay. So taking this over here, this is our unit vector AG. And we're gonna do the dot product of these with the cross product that we already did. So what that's gonna look like is it's gonna be unit vector of AG dotted with R cross U. So that's gonna be 0.64, 0.64, and then multiplied by negative 3.045, and then we're gonna have plus 0 times 0 for the J direction, and then we're going to have plus negative 0.768 multiplied by negative 2.54. And that is going to give us a distance of approximately 0.0114 meters. So here, since we know that the moment that's being generated about this axis is equal to 1,020 Newton meters, and we know that the distance that P is acting at is a distance of 0.0114 meters, then we just rearrange to solve for P by doing 1020 divided by 0.0114. This is Newton meters, this is meters, and we get approximately 8.9 times 10 to the 4 newtons, which is 89 kilonewtons. And that's the solution for that problem.
All right, now we're going to move on to problem 4. In this one, we are finding the moment that this force P provides about the line OD. And to do that, we're going to use the cross product. So to use that cross product, we're going to need 3 different vectors. We're going to need the unit vector of this line OD, a line that connects O, or this line OD, to the force, and we're going to use for this the origin to the point B. And then finally, we're going to need the force P, but in vector format. So let's start out with the line OD. First, we're going to write it in just its standard vector form in Cartesian format. which gives us our OD. And in the X, we have 0.25 meters. In the Y, we have 0.2. And then it's 0 in the Z. Then we're going to take the magnitude of this force, or of this vector, which is the square root of 0.25 squared plus 0.2 squared. And then since the last one is 0, and this is going to give us 0.32. And then we're going to divide our vector by this magnitude to get the unit vector of OD, which gives us 0.781, 0.625, and 0. So we're going to save this for later. Next, we are going to find that line OB. This one's pretty simple. That's why we chose it, because it's 0 in the X and the Y. So we only have that Z component. And it's going to be 0.3. And this is going to make our cross product later on much easier. And then finally, we're going to find the vector of that force, starting with its Cartesian coordinates, which are 0.25 in the X, 0 in the Y, and then negative 0.3 in the Z. And then we're going to take its magnitude, which is the square root of that 0.25 squared plus the 0.3 squared, which then gives us 0.391. And then we're going to use that magnitude to find the unit vector, which gives us 0.64 in the X, 0 in the Y, and then negative 0.768 in the Z. And finally, we can multiply the magnitude of that force P, which is 125 newtons, by the unit vector to get the vector format of the force P. And this gives us 80.02 in the X, 0 in the Y, and negative 96.03 in the Z. So we've got our 3 important vectors, and then we can set up our cross product. So the moment about OD is equal to the cross product of our unit vector of OD, which is 0.781, 0.625, and 0. And then we have the vector that connects the force and the line, which is 0, 0, 0.3. And then finally, we have that force, which is 80.02, 0, and then negative 96.03. And we can evaluate that cross product. We take the 0.781, and since both of these are going to be 0, that term just cancels out. So we're going to have 0.781 times 0, and then we're going to subtract 0.625 times, we've got a 0 term here, and then we've got 0.3 times 80.02, but since that's our second term, we're going to put a negative in front of that. And then we've got plus 0 times some value, but that's just going to go to 0 anyway. So this comes out to negative 0.625 times, and then that negative 0.3 times 80.02 is negative 24.006, which comes out to 15 Newton meters. So our moment about line OD by force P is just 15 Newton meters. And then we're going to move on to problem 5. This one's pretty simple. There's 2 ways to solve it. First, we're going to do the slightly longer approach, and then we're going to do the simplified, easier one. That's just a little less intuitive. So we're trying to find the moment about point O that these 2 forces apply. The easy way to do that, since they are both on the y-axis, we know the perpendicular distance. So the moment about point O is equal to 4.5 times 20. And that is going to be in the negative direction. And then we've got 5 times 20 for our other force. And if you do that math, that just comes out to 10 uh, kilonewton meters. Let me double check that. Yeah, that's going to come out to 10 kilonewton meters. Another simpler, easier way to do this is that if you realize these two forces are parallel, you can actually treat them as couple forces, which create a couple moment. And so the equation for that moment is just the value of the forces times the distance between them. And that's going to come out to 20 kilonewtons times 0.5 meters, which gives us 10 kilonewton meters, which as you can see is the same as we got above. The nice thing about this method is that if they ask us to find the moment about any point on this plane or on this 3D system, it would be the same. It's going to be that 10 kilonewton meters because they're a couple moment. So they could give us this point and we can call it Z. And no matter where Z is, it's still going to be 10 kilonewton meters. And they don't even need to give us the geometry of where it's located. So that makes it really convenient to solve complex problems.
Okay, thank you guys for coming to the review session. If you guys have any questions, you can reach out to us at the tutoring centers. The Pulse email should be found online. If you look up Pulse Engineering Tutoring Center, you can reach out to us with any questions. We're located in ECG 152 for MAE tutoring and ECG 104 for any CSE tutoring. Thank you guys.